Section 11.1, sequences. So this whole chapter talks about sequences and series. Not a lot of integrals involved, a little bit, but mostly something totally new. When we go to section 3, we're going to use integrals a lot there, but not in most of the sections as we did before. So here we introduce what a sequence is. So let me start by a definition. What is a sequence? So a sequence, back in elementary school, we defined it as a list of numbers. But in calculus is defined as a function whose domain is the set of natural numbers, or we call them counting numbers, starting at 1. Okay, so for example, like 2, 5, 7, 9, 11, etc. This is a sequence. This is called, let's call it A sub 1, A sub 2, A sub 3, A sub 1, A sub 2, A sub 3. This means the first term, second term, third term of the sequence. They don't have to be always like that. We can look at another example, say 3, 2, negative 1, 1 half, 0.4, 7, da-da-da. That's called 11. So again, this is the first term, second term, third term. At the nth position, that's called the nth term of the sequence. And when we work with sequences, the notation for the sequence, some people might write a parentheses like this, or some people might use this, that's when the braces, or simply just an is called the nth term of the sequence. So let's look at this sequence as an example. The square root of n plus 1, and I'm going to write n equals 1 to infinity. What does that mean? That means an is the square root of n plus 2. So if I like to write or find the first term, all I do is just plug in n1, so that gives me square root 3. That's the first term of the sequence. Even if it's not specified, n is always bigger than or equal to 1. Unless if specified otherwise. Sometimes they might start at 10. So n2 is going to be the square root of 4, but please make sure you simplify it. a3 is the square root of 5, and so on and so forth. Another example, negative 1 to n plus 1, n over n minus 1, n runs from 2 to infinity. Maybe I can ask you list the first 3 terms of the sequence. So again, this tells us that an is negative 1 to an n plus 1 times n over n minus 1. Notice the first term here is going to be when an equals, or a2. That's the first term because n starts at 2. So you need to substitute n2 to see what we get. We get negative 2. Do you see why I start at 2? Because if n starts at 1, you will get 1 over 0. So a3, that would be 1 times 3 over 2, so 3 halves. a4, negative 4 thirds. Now, at some point, if this sequence, the more numbers you list, the more you think like, oh, it's approaching a specific value, then we say the sequence converges. If it goes to infinity or does not exist, then we say it diverges. You're gonna hear me saying converges, diverges a million times in this chapter. So if we look at this sequence an, let's say it's 3 plus negative 1 to an n, such a sequence has terms. See, we don't know what n is, so it means 1, n starts at 1. If you put 1 in, you get 3 minus 1 is 2. If you put 2 in, you're going to get 3 plus 1, 4. And then it's going to keep 2, 4, 2, 4, etc. So it alternates between 2 and 4. So it's not heading to a specific value. So we say the limit of this sequence does not exist. So you can say limit of an as n approaches infinity does not exist. So we say the sequence diverges. Recall some properties from limits that we're going to be using here. If we let the limit of an as n approaches infinity, let's say L, and limit of bn as n approaches infinity is k, then first one, the limit of an plus bn as n approaches infinity is the limit of the first one, which is L, plus the limit of the second one, which is k. B, the limit, of course the difference would be the same. Now the product as n goes to infinity, that's going to be L times k. C, limit as n approaches infinity for any constant c times an is going to be c times L. C is a real number, so c belongs, this e looks like belongs to R, means c is any real number. If we're doing an over bn as n approaches infinity, that's going to be L over k, provided that k is not 0, neither bn. Those are the standard limit laws that we learned in Calc 1. So if they ask us find the limit of an as n approaches infinity, if an is given as, we take a very easy one, 2n over 1 minus n. So basically, we're going to find the limit of an, which is 2n over 1 minus n, as n approaches infinity. If you try to pass the limit, you can do limit on top and on the bottom, that's going to go to infinity over negative infinity, which is indeterminate. So one way to do that, you can use L'Hopital's rule by finding the derivative of the top, derivative of the bottom, or you can divide top and bottom by n. You get 2 over 1 over n minus 1. This will go to 0, and that would give us 2 over negative 1, which is negative 2. Another example. Let's make it more challenging. Say n squared 2 to the n minus 1. And the question is find the limit of an as n approaches infinity. Okay, so to go over this one, we find the limit of n squared 2 to the n minus 1 as n goes to infinity. This would go to infinity over infinity, which is indeterminate. I think dividing top and bottom by n squared or n is not going to be easy. We can use L'Hopital's rule. Derivative of n squared is 2n.
derivative of 2 to the n is 2 to the n times natural log of the base times the derivative of n, which is 1, minus the derivative of 1 is 0, and this still gives us infinity over infinity. We can use L'Hopital again. Derivative of 2n is 2 to the n times a natural log of 2 times the other natural log of 2. So the denominator grows so fast, goes to infinity, so this is going to go to a number over infinity, which is 0. So we say that this sequence converges, it converges to 0. Now if we have an, a sequence an less than or equal bn less than or equal cn for some n bigger than or equal some n0, n0 could be like any positive number, and the limit of an as n approaches infinity equals the limit of cn as n approaches infinity, and let's say gives me L. Then the middle one, which is the limit of bn as n goes to infinity, is L. That's what we call squeeze theorem for sequences. The same one we introduced in functions back in Calc 1. We're going to go over several theorems in this section and definitions for new terms that we're going to be using throughout the chapter. So the first one is, let's call it a theorem here. It says if the limit as n approaches infinity of the absolute value of an is 0, then the limit of an as n approaches infinity is 0. So again, if the limit of the absolute value goes to 0, then the limit of an itself goes to 0. Let's look at an example. If we are asked to find the limit of negative 1 to an n, negative 1 to n over n as n approaches infinity, what do? We try to find the limit. We find the limit of the absolute value of negative 1 to an n over n. So note the denominator is positive all the time here, the n. So I'm not worried about that part. When you do the absolute value of the top, negative 1 to an n, that will be 1. So this will go to 0. On the side, negative 1 to an n or negative 1 to an n plus 1, when you do absolute value for each, that will give us 1. Even negative 1 to an n minus 1 still. So absolute value of negative 1 to an n minus 1 still gives us 1. So what happened here is I try to find the limit of this when n approaches infinity, it gives me 0. Then by the above stated theorem, the limit of negative 1 to an n over n as n approaches infinity is also 0. Now we move on into what we call monotonic sequences. Monotonic sequences. We say a sequence, call it an, is increasing if, let's see, let me show you. So let's say we have the sequence increasing like this. This is n plus 1. So if we project it up, this is an. This is an plus 1. Notice it's an increasing sequence. Increasing goes up from left to right. So the sequence is increasing if, notice, an plus 1 is bigger than or equal an for all n bigger than or equal to 1. We can say the same thing. We can define a sequence an is decreasing if an plus 1 is less than or equal to an, again for all n bigger than or equal to 1. Now, what did you say monotonic? Why you started with monotonic? Well, now we say a sequence is called monotonic if it is either increasing or decreasing. To practice on this, determine whether each sequence having the given nth term is monotonic. Part A. An equals 3 plus negative 1 to an n power. Is this sequence monotonic? Think about for 1 minute.
So this one, we worked with this one earlier. When you plug in 1, 2, 3, 4,
this alternates between 2 and 4 in value. So it is not monotonic. Not monotonic. Part B, let's call it Bn. It's 2n over 1 plus n.
how do we check if this is monotonic? We cannot just like select values and say, yeah, it's always increasing or always decreasing.
So remember, the main definition was a sequence is increasing if a sub n plus 1 is bigger than or equal to a sub n. Okay. So one thing motivates us here to start is probably I want to find b sub n plus 1. So replace every n with n plus 1. That would give us 2n plus 2 divided by n plus 2. Now the question, how do I know is b sub n plus 1 bigger than or equal to bn? How do I know? Well, this is how we do it. So it's the same way as asking, is this bigger than or equal to n over 1 plus n? Now we can multiply both sides by the LCD because n is positive. It's not going to affect the inequality sign. So that means 2n plus 2 times 1 plus n. Is that going to be bigger than or equal to 2n times n plus 2? Well, then distribute all of this. You get 2n squared plus 4n plus 2. Is this bigger than or equal to 2n squared plus 4n? If you subtract 2n squared on both sides and 4n, that will leave us 2 bigger than or equal to 0. Is that true? Yeah, that's true. Since bn plus 1 is bigger than or equal to bn, then we can say that the sequence bn is monotonic. It's increasing. So increasing, hence monotonic. So that's one way to test if a sequence is monotonic or not. Another way, as a second method, how do we check if a sequence is monotonic? So this is the given sequence. We can rewrite this as a function in x, replacing the n's with x's.
Why did we do that? Well, because when I'm talking about increasing, decreasing, we learned something back in Calc 1 where we deal with derivatives. So we find the derivative for this using quotient rule. The bottom one times the derivative to the top minus the top times the derivative to the bottom. So if we calculate this, that would give us 2 over 1 plus x squared. Notice this is always bigger than 0 for all x. So that tells us it's in increasing. So that's another way to look at it. Again, as I said earlier, we're going to look at more definitions and theorems here. One other definition is called bounded sequences, or has to do with bounded sequences. The first one, we say a sequence an is bounded above if there is a real number, call it capital M, so that an is always less than or equal that capital M for all n. I think that makes sense. Like, to call that an upper bound, all the values have to be less than or equal that M. That's the upper bound. Now, a sequence, same sequence, an is bounded below if there is a real number, small m, so that small m, so that an is bigger than or equal small m for all n. 3. A sequence is bounded if it is bounded above and below. So it will look like this: an is bounded by small m and capital M. That's called bounded. So it doesn't go to infinity on the top or the bottom. It doesn't go forever. So now, why do we need to know this? Well, that will motivate us to introduce a theorem. The theorem said if a sequence is bounded and monotonic, then it converges. So it has to be both bounded and monotonic in order for it to converge. Can we take a look at an example? Say an is 1 over n. Is this sequence, does it converge or diverge? Well, let's see. First thing, if we pick values, just like if you start like trying to analyze this sequence, pick values for n, say n 1, 2, 3, 4, 5. So that would give me 1. So notice 1 is the maximum value this can be, because n is the smallest. That would make, because that would be 1/2, and then 1/3, 1/4, 1/5. It's getting close and close, like getting closer to what?
So as we notice, as I increase n, an is approaching, which is 1 over n, is approaching 0. So we say that this sequence, the sequence an, is bounded above by 1 and below by 0. Now, is it monotonic? Well, let's see. They give us an 1 over n. So from here I find an plus 1. And we know, because these are positives, the larger the denominator, the smaller the fraction. So an plus 1 is less than or equal an for all n. That tells us that the sequence is decreasing. Decreasing means monotonic. Now what I did, I proved it's bounded and I proved it's monotonic. Then an is bounded and monotonic, and hence converges by the above theorem. How about if we go over another example? n squared over n plus 1. Does it converge?
So the first thing, what happens when n goes to infinity? That's what we did in the previous problem or example. When n grew to infinity, then the 1 over infinity went to 0. So it was bounded by 0. And the maximum value was 1. So we knew it was bounded. Now the first thing I would do, I want to find, as n goes to infinity, what happened to this sequence? N squared over n plus 1. This would go to infinity over infinity. We can use L'Hopital's rule, 2n over 1, which goes to infinity. So notice it's going to go to infinity, so that tells me it's not bounded. And since one of the conditions failed to work, the sequence does not converge, or we say is not convergent. Language does not converge or is not convergent. Notice, if you try to find the derivative for this one, note this sequence is monotonic. If you try to find out this, find the derivative and you will see. If we look at another example, say an equals just -1 to an n. Notice, if you take n1, n2, n3, n4, you notice this sequence, if n is 1, you're going to get -1, n2, you're going to get 1, -1, negative 1, 1, -1, 1, -1, 1, all the time. So it is bounded by -1, 1. But if you try to find the derivative for this, or you try to find an plus 1 and things like that, it is not monotonic. So, not divergent. So both conditions of the theorem should be met in order for the sequence to converge. Other things good to introduce in this section about recursive sequences. What are recursive sequences? Let's say an given, a1
is 3, and an plus 1 is n plus 1 over 2 times an. Find a2. So notice the least value I can pick is 1, n equals 1. So you get, that gives me a2 is 1 plus 1, 2 over 2 is 1 times a1. So it's 1a1. So that's going to be 3. It's given. Now if I take n2, that's going to give me a3 is 2 plus 1, 3 over 2, a2. But a2 we just found it. a2 we found it 3. So that makes it 9/2. So you notice how the sequence, the nth plus 1 term, is defined in terms of an. That's called recursive sequences. We can look at other examples. Say a1 is 5 and an plus 1 is 2 plus 3 a sub n. Find, let's say, a sub 3. They only give me a sub 1. So if I take n1, that will give me a sub 2 because 1 plus 1. 2 plus 3 sub a plus 1. They give me a sub 1, 5. So that would be 17. A sub 3, plug in n2, you get 2 plus 3 a sub 2. So that would be 2 plus 3 times 17. So 51 plus 2 is 53. That's a sub 3. So we found a sub 3, we found a sub 2. So these are recursive. Another example on this, which is very popular, is called Fibonacci sequence. Fibonacci So Fibonacci defined, you can say an or f sub n, is defined by the conditions f sub 1 is 1, f sub 2 is 1, and f sub n is f sub n minus 1 plus f sub n minus 2 for n bigger than or equal to 3. That's called Fibonacci sequence. They give you the first two terms, not just the first one. So if I want to find f sub 3, for example, I substitute n3 here, here, and there. So f sub 3 is f sub 3 minus 1, 2, and f sub 1. So 2 is given, 1 plus 1 is 2. Then if I want to find f sub 4, substitute n4. So you're going to get f sub 3 plus f sub 2. So 3 we just found it, and that was 1, so you get 3. And you can look at this, how the pattern works. The first term they give us 1, and f2 is 1. We found f3 2, and the next one 3. So basically you add the last two terms to get the following one. So if I add 2 plus 3, you get 5. You add 3 plus this, 8, then 13, and so on and so forth. That's called Fibonacci sequence. Also, while we're working throughout this chapter, we need to learn a little bit more of some tools we learned in pre-calc, but are important in this chapter. For example, we can recall factorials. So if you have like 3 factorial, the exclamation mark means factorial. So that's 3 times 2 times 1, 6. By definition, 0 factorial is 1, and 1 factorial is 1. In general, if you have, if you want to find n factorial, is defined as n times n minus 1, n minus 2, all the way down to 3 times 2 times 1. Simplify. Say 10 factorial over 8 factorial. So we can do 10 factorials, 10 times 9 times 8, and that keeps going down to 1. Same thing with 8, but usually you keep the smaller the same. So 8 is smaller than 10. We keep it as is, 8 factorial. And then the 10 factorial goes as 10 times 9 times 8 factorial. Stop there. So the factorials cancel, and that gives me 90. It's better than going all the way down to 1 for each one of them. Not only number-wise, you know, maybe we can ask you what's 2n minus 1 factorial divided by 2n plus 1 factorial. So again, we keep the smaller the same. So the top is the smaller. The denominator we write as 2n plus 1, subtract 1, you get 2n, subtract 1 again, 2n minus 1 factorial. So these cancel out. So that gives us 1 over 2n times 2n plus 1. Not only factorials, but sometimes it would be good to see how to write, let's say, write an expression for the nth term, of the sequence. Let's say 1 comma x squared over 2 comma x to the third over 6 comma x to the fourth over 24 comma x to the fifth over 120. Basically, we need to find a pattern here. So we want to find an. On the top, I see it looks like x to the n. Like if n starts at 0, you get x to 0, which is 1, and 1 you get 1, and 2 you get 2. Let's see the bottom one. It's like 1, 1, then 2, then 6. Oh, what is that? It doesn't look like a pattern, like 2n or 2n plus 1 or 3n plus 1 or minus 2. But if you look at this is 1, 1, then this, if you try the factorials, like 0 factorial is 1, 1 factorial 1, 2 factorial 2, 3 factorial 6. Oh, it looks like it's coming out. 4 factorial, 4 times 3 times 2 times 1, 24. Oh, that looks like it's n factorial. Now, you might say, wait, why n starts at 0? I mean, n here, we are just trying to generate a formula for that. N could be anything. Now, can I make n starts at 1? Yes, you can. Now, what would be, so I'm going to say or, what would be the answer? So when you made n bigger than or equal to 1, just so you know how I'm thinking about it. So it's kind of like, to get 1 on the right side here, I want to get 1. It's kind of like I want to add 1 to both sides or something. I want to add 1 to both sides. Just think this way a little bit. Now what happens is, if I want to go back, so this is called shifting. This is called shifting. So if I want to get x to the 0 on the top, so that would be n minus 1. So when you substitute n1 minus 1 is 0, so you get x to 0. Then you do the same thing on the bottom. Instead of just n, you do n minus 1 factorial. So that's called shifting. You can take any sequence and shift it. To the right, to the left, you do minus 1 or plus 1. So this is the expression that we're looking for. So this is the nth term of the sequence. This is the nth term. So all of this was introduction to sequences. Okay. Introduction to sequences. So in sequences, again, we learned what a sequence is, what are the terms of the sequence, if it's increasing or decreasing, how do we prove or find out if a sequence is increasing or decreasing, and if it's increasing or decreasing, we call it monotonic. Then we looked at how to prove or what is mean to say bounded sequence, and then we looked at a theorem. If it's bounded and monotonic, then it is it converges, because the whole chapter is going to teach us mostly how to check if a sequence converges or diverges. And then we introduce small things like a theorem of if the limit of the opposite value converges or converges, then the limit itself it converges, like, or the theorem that we stated before we talked about, you know, monotonic sequences and bounded stuff. That was like a quick theorem here. That was if the limit is 0, then of the opposite value, then the limit of the sequence itself is 0. And we went over other small things such as, you know, factorials, how to work with them, how do you simplify factorials, how you use them to find or write the nth term of the sequence, and other things.